Hey everyone, Mr. Fransky here. Today we're going to be looking at the Fundamental Theorem of Calculus Part 2. So hopefully you've watched the Part 1 videos already and you kind of have this idea of the accumulation function down. You have the idea that the derivative of an integral is kind of undoing itself. It gives you back the original function. And today we're going to talk about Part 2 and how we can use antiderivatives to solve integrals. So some key vocabulary: antiderivative, that's something we've thrown around a little bit but haven't done a lot with. And then fundamental theorem of calculus part 2, of course, and integral as net change in a function. So we've been kind of throwing this word antiderivative around, and it's a valid question to say, what the heck is an antiderivative? Because we haven't really dealt with them. We've kind of said, you know, you can use these to evaluate integrals, but we haven't shown why, and we haven't really talked about what it is. So the whole point is, if you have, like, let's say f of x is x squared. We did this all of chapter 3. That means f prime of x would be 2x, right? So what we just did was we took a derivative. So that is a derivative. So an antiderivative happens when you go backwards. This is an antiderivative. So at a very base level, you're just saying, this is the derivative of some function. What function is it? Well, this is the derivative of x squared. Let's try with some other stuff. If, let's say, I don't know, f of x is sine x, then the antiderivative, so I'm saying sine x is the derivative of some function. The antiderivative would be the antiderivative of sine x. So I think something that makes the derivative of sine. Cosine gives you negative sine, so it'd be negative cosine. The derivative of negative cosine, sine x. So negative cosine x is an antiderivative for sine x. So why is this important? Because let's think about what fundamental theorem of calculus showed us, the first part. They told us that if f of x is defined as the integral from a to x, f of t dt, then f prime of x, which is the derivative of integral a to x, f of t dt, is equal to lowercase f of x. So let's just write these two pieces together. We showed that capital F prime of x is equal to lowercase f of x. So what that means is if f of x is the derivative of capital F, this means that capital F of x is the antiderivative. Antiderivative for lowercase f of x. Okay? So what this means is when you do the accumulation function, we know the derivative of it is the graph that you are actually integrating. That was kind of mind-blowing to begin with. But what this means is that f of x must be the antiderivative. It's like we're going backwards. So we're taking this derivative, gives us f of x, so then the antiderivative brings us back. The antiderivative brings us back from f of x to f prime of x. Now, there is not always only one antiderivative. Like, for example, let's say we're using cosine just to make things simpler. So if, let's say lowercase f of x is cosine x, and we want an antiderivative for it. Now the simplest one would be f of x, so we'll use capital F for antiderivative. The simplest one would be sine x, right? Because the derivative of sine x is cosine x. So the antiderivative of cosine, definitely sine. Now tell me if this would work. What if I did sine of x plus 6? Is sine of x plus 6 also an antiderivative for cosine x? I think so, because the derivative of sine of x plus 6, that plus 6 just disappears when you take the derivative, so you get cosine. So what happens here is you get a whole family of functions, right? Basically, anything that's sine x plus some constant, we'll call it c. This might be your first plus c of calculus. So capital F of x is an antiderivative, and that's why you say an antiderivative. Usually you don't use this word, the antiderivative. We use it initially because it's like, okay, we're looking for something whose derivative makes this function. But for any function, if you're looking for an antiderivative, you can add any constant you want. Sine x plus 6 or 7 or 12 or 5,682 or e or pi. All of those are constants that when you derive will disappear. So this is kind of the way to go. When you're looking for a general antiderivative, you can add any constant you want. So how do these help me? Well, the whole idea is then that we're looking for some kind of an antiderivative. So we have this capital F of x is the integral from a to x, f of t dt. And really, what we can do here is, because f prime of x is equal to lowercase f of x, we know that capital F of x is going to be the antiderivative. So what we can do is we can get this idea of a family of functions. So this means that the integral from a to x of f of t dt is equal to the antiderivative f of x plus c. Okay? So what's happening here is this lowercase f right here. This is our function, right? The function that we're taking the integral of, so we're accumulating it. And this capital F of x is some antiderivative because of this relationship between f and f prime, right? Basically all we're doing here is we're integrating both sides of this. The integral of the derivative is the integral of f of x. Right? So we have an antiderivative here, and it could be adding any constant that you want, and that's got to be equal to the accumulation function of our function f of t dt. So we're going to use one of our integral properties here. The integral from a to a, okay, so the integral from a to a of f of t dt is going to be equal to f of x plus c, but that's actually, we're putting in a for x. So f of a plus c, and if you integrate from the same value to itself, that has got to be equal to 0. So we're going to kind of steal this part of the equation on the right here, and we're going to subtract c. Sorry, we're going to subtract f of a. So this means that c is equal to the opposite of f of a. So we basically just solved using one value that we know information about. If you integrate from a to itself, it's going to be 0. So we have that our c value has got to be negative f of a. So we'll plug that back into here. So we have integral from a to x of f of t dt is equal to f of x, and now that we have this solved for, it's minus f of a. So whatever your a value is, if you plug that into the antiderivative, that is going to be your c value, the opposite of it. So now we're going to get a formula for any integral you ever have. The integral from a to b of f of t dt is equal to, well, if x is b now, capital F of b minus capital F of a. Since that t is a dummy variable and we now have no x's left, we're going to swap it out for an x. So we have integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So let's think about what we just realized. This tells us that the area from a to b of any curve you want, a to b, if this guy right here is lowercase f of x dx, to find that area, there's a relationship between f of x and its antiderivative. All you have to do is find any antiderivative, capital F, plug in the b value, plug in the a value, subtract them, and it's going to exactly give you that area. That is pretty cool. It gives us a really powerful tool to be able to find area under curves. So here is the fundamental theorem of calculus part 2 itself. So if we have f of x is a continuous function, and capital F of x is any antiderivative, and we'll talk about why it doesn't matter which one you pick, any antiderivative for lowercase f of x, then the integral from a to b of lowercase f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, because that's what we found out that constant was. I'll make that a little clearer there. This is fundamental theorem of calculus part 2, and it is so useful because it gives us a way to evaluate any integral from a to b of a function if we can find an antiderivative. And that's it. So that's fundamental theorem of calculus part 2. Let's take a look at some examples. So we want to integrate from -1 to 3 of 3x squared plus 1 dx. So 3x squared plus 1 will be shifted up, and it'll be a skinny parabola. Going from -1, let's say that's right here, to +3, let's say it's like right here. So we want to find this area. Now that area is not something they taught you in geometry, right? But what we just learned is if we find an antiderivative for this guy, then it's going to be able to find the area by plugging in two values. So we need an antiderivative. For 3x squared plus 1. Now this takes a little bit of practice, and we'll learn kind of some general formulas for this. But the point is, all we have to do is think, okay, what is the thing that this is the derivative of? Well, remember, the power is always decreased by 1. So this must have started as some kind of an x cubed. And hey, that actually works out really well, because the derivative of x cubed, the 3 comes to the front, and the 3 drops down to a 2. So that's it. And then the derivative of what gives me 1? Well, this is a constant, so I'm going to need a linear function, and it's just x. So this takes some practice, takes a little bit of time. But this is an antiderivative for 3x squared plus 1. It is the simplest one I can think of. We could add a constant. I'll show you that it works in a second. But all you have to do is find an antiderivative, and x cubed plus x will work. So that means all I have to do is plug in the 3. So I'm going to do f of, so let's call this capital F of x. That's our antiderivative. So f of 3 minus f of -1. So that's going to be 3 cubed plus 3 minus f of -1. -1 cubed minus 1. So 3 cubed is 27 plus 3 is 30. Minus -1 cubed is -1 minus 1 more is -2. 30 plus 2 is 32. So that area underneath the curve between -1 and 3 is exactly 32. Now let me show you why it doesn't matter which antiderivative we choose. Let's say we chose x cubed plus x plus 7. Right? Because you can add any constant you want, and it's still an antiderivative. Because you take the derivative of this, it's still 3x squared plus 1. Let's try plugging it in and see what happens. So f of 3 minus f of -1 would be 3 cubed is 27 plus 3 plus 7. Then we subtract off, -1 cubed is -1 minus 1 plus 7. Notice what happens to the 7s. You subtract it off. Every time you do f of b minus f of a, if you have a plus c here and a plus c here, no matter what constant it is, the subtraction will take it away. So the point is, you might as well just use the simplest antiderivative, because otherwise you're just adding more work for yourself when you're subtracting. Either way, you'll get 32. Just more algebra mistakes happen when you start adding weird constants. Let's try another one. Integral 0 to pi of sine x dx. So we need an anti for sine x. We talked about this before. Antiderivative for sine x is negative cosine x. So negative cosine x will work. So we're going to do f of pi minus f of 0, which is negative cosine of pi minus cosine of, plus cosine of 0, because it's negative cosine. Cosine of pi is -1, so we have a positive 1, plus cosine of 0, which is 1, equals 2. We've seen this a few times. 0 to pi of sine, area of 2 underneath there. Once again, the trig functions and how they relate to each other is pretty cool. I think I might have one more. So we want the total area. The reason I bolded that is because total area is always positive. Always positive. So even though we see we have some part that's above the graph here and some part that's below, what we're going to do is we're going to have to split it up, find the integral of each piece, and then add them together, because area is always positive. If they ask for an integral, that has sign, S-I-G-N. So integral has sign. It'd be area above minus area below. Area altogether, you have to figure out which parts are above, which parts are below, and then add them together. So for this guy, we're going to have to integrate from 0 to 2 of 4 minus x squared dx. And then we'll deal with the bottom part in a second. So we need an antiderivative for this. So an antiderivative for that looks like 4 would be 4x. And then minus, so the derivative that makes x squared is going to have to be some kind of x cubed. But when the 3 comes to the front, I need it to cancel out. So it's got to be x cubed over 3. Then the 3 will come out, cancel out, you'll have x squared, and you'll have a 4x. Could add a constant, but it makes our life harder, so we won't. So we have our antiderivative, 4x minus x cubed over 3. We'll plug in 2 and 0. So we have 4 times 2 minus 8 thirds. Minus, hey, when I plug in 0 here, 0. Beautiful. So this gives us 8 minus 8 thirds. 8 is 24 thirds minus 8 thirds, which is going to be 16 over 3. So that's the top part here, 16 thirds. Now let's figure out the bottom. So we do that by integrating from 2 to 3. 2 to 3 of 4 minus x squared dx. So we have our antiderivative, so it's going to be 4 times 3 minus, 27 thirds, which is 9. And then we subtract off plugging in 2. Well, we already did that once, so we're going to subtract off 16 thirds. Right? When we plugged in 2 here, we got exactly 16 thirds, so we don't have to do that math again. So we have 12 minus 9 minus 16 thirds. 12 minus 9 is 3. That's 9 thirds minus 16 thirds, which is negative 7 thirds. Now, it makes sense that it's negative because it's down below, but I want area, so I'm going to do a positive 7 thirds. Add them together, 16 thirds and 7 thirds, 23 thirds is going to be our total area. Pretty neat. So, this idea that we can find the area under any curve by using a change in the antiderivative, just subtracting those two pieces, the f of b minus f of a, very powerful. Very powerful. So this tells us that the integral, the area, actually tells us how much the antiderivative changes over an interval. I'm not sure if I have another slide on here. I do, and I want to show you one thing on here, which is good. So your homework, 5.4 and 5a, are both going to be due on Monday. I'll see you then. Also, if you want to get the green packet, it has a whole bunch of AP problems. I think there are 6 of them. And they're similar to the one I showed at the beginning of this video. So I think they're fun. Make sure you do your tower of functions. I always do tower of functions, the accumulation function, a to x, and then you have the derivative, and that's equal to the actual graph itself. And then the second derivative, which tells you about inflection points and concavity, that's actually the slope of the graph. So I want to talk about one more thing I talked about at the end, where I was talking about the change in the antiderivative. What started this whole thing, we looked at a velocity graph, and we said if it goes straight up, we can find the change in distance by looking at the area underneath. And that makes sense to me, because if we integrate v of t, it should be a change in the antiderivative. Well, the antiderivative of velocity is position. So it'd be s of b minus s of a, which gives you the change in position exactly. So it all comes together, and it's so cool how these two fundamental theorem pieces work together and how they're going to really form the rest of the year. All right, and that's everything. So lots to digest. Very important theorem that we learned today. Being able to use this fundamental theorem of calculus both to look at accumulating functions and also towards using the antiderivatives in order to find values of integrals. So cool stuff. I will be using it a lot. So if you feel like you're lost and your head is spinning, it's okay. We're going to do lots of practice with it. But that's all she wrote. So I love you guys. That's why I'm here. Have a great day.